In section 18.4, we examine Claisen rearrangement because it's a reaction of ethers. So in the classic Claisen rearrangement, the aryl ether, specifically the allyl aryl ether, and of course we can prepare those in a very straightforward manner from allyl bromide and sodium phenoxide. Of course, we get sodium phenoxide by just treating phenol with sodium hydroxide. Simple SN2 displacement produces this. Now, this compound undergoes a stereospecific reaction that's closely related to the Diels-Alder reaction. When we heat this up, and I'm going to go ahead and push the arrows for the mechanism here because I think it's important for you to see how this works. We're going to swing that pi bond out to make a carbon-carbon single bond. This bond swings up, and this bond, the carbon-oxygen bond, breaks. Now, I hope you see that cyclic flow of 6 electrons like we see with benzene. It causes us to have an aromatic character in the transition state, thus lowering the energy barrier, and also the flow of 6 pi electrons through the system like we saw in the Diels-Alder reaction. So what would this produce? Well, it produces an intermediate that's unstable. If you follow the arrows I drew directly, we produce this species where the allyl group is now on what was the ortho position of the aromatic ring. Now, this compound is unstable because you see we've lost aromatic stabilization. And since we've lost aromatic stabilization, this is no longer an aromatic compound, and so it's the keto form of this particular compound, but it rapidly and effectively irreversibly converts to the enol form so this proton shifts position over to the oxygen, and then here you see we have an alkene and an ol. So this is the enol form of this, and this is the product that we can isolate from the Claisen condensation. So again, this cyclic transition state that has aromatic character lowers the barrier and facilitates this process. Now that if you've already had the chapter on aldehydes and ketones, you will learn more about that keto-enol tautomerization. Now, if we look at this species, what we see is we have an ene ether and an allyl ether. Okay? So the minimum features that we need for this chemistry are an ene allyl ether. Okay, we call it a vinyl. This is the vinyl group, allyl 1, 2, 3 in the allele. I'm going to put a substituent on here because these are useful in this process and because I want to identify the different atoms 4, 5, and 6. And so these will also undergo the Claisen condensation. So if that happens, let's push the arrows and see where they go. There. We swing this one up. We're going to make a carbon-oxygen double bond. We're going to break this bond. And And I'll keep the atoms in a similar arrangement. We make a new product. In this case, the product is an aldehyde because I had a hydrogen here. That could have been an alkyl group, in which case we'd have a ketone. And so we can get these from these vinyl allyl ethers. Okay. So I'm going to draw this product in a slightly different way. So when we have a 1, 2, 3, 4, 5, when we have a 4, 5 aldehyde or ketone, this could have been R, in which case this would have been R and R. When we have an alkene, let me improve that alkene illustration. When we have that alkene at the 4 and 5 position, that's a clue that we want to go back to this compound. Now, how do we get that? Well, we haven't learned the chemistry quite yet. I think that's coming up about chapter 22 or 23, and we'll learn how to control this alpha position and be able to make those substrates. So that's section 18.4, ether reactions, the Claisen rearrangement.